So we just talked about the fundamental forces. In this clip, we're going to talk about the phenomenological forces. And by phenomenological forces, I mean the forces that we actually conventionally talk about a lot, like friction and springs and drag and so on and so forth. But the idea is that a phenomenological force is due to fundamental interactions but is better modeled by some simplified model. Okay, so a good example of this is friction, right? If you think about friction now at a microscopic level, if I actually sort of think about, okay, I've got some surface, I've got my, a book or a block or whatever on that surface, and I'm trying to push that block across the surface. If I actually zoom in on this, right, and get down to the very sort of microscopic level, and obviously this is a much bigger zoom than I'm indicating here. Now, fundamentally, what I have here is one object that's made up of all kinds of nuclei and electrons that are orbiting, well, not orbiting, but electrons that are in wave functions around those nuclei inside the book. In the surface that book is on, there are also all kinds of atoms consisting of nuclei and electrons in complicated ways, and all of those electrons and nuclei in the book are interacting with each other to hold the book together and are interacting with this table, and there's some amount of bonding between the electrons, between the atoms in this book and the atoms in the table that makes it difficult to push the book across the table. When you try to push the book across the table, in order to do so, you actually need to break some of the bonds that are holding the book to the table. So fundamentally, what's going on in friction is that you have an electromagnetic interaction between atoms in the book and atoms in the table, and that electromagnetic interaction makes it hard to move the book across the table, and makes it hard both to get the book started moving, and also as you continue to move the book across the table, there's still bonding that happens that you need to break, and so that it takes work to move the book across the table as well. Okay. So that's what's happening on a microscopic level. On a microscopic level, another thing that's happening is each time you break one of those bonds, you sort of stretched a bond and then you've broken it, and the atom sort of shakes back and forth. That adds some thermal energy to the book and to the table. So as you slide the book across the table, you're going to heat up the interface between them. So there's a lot that's going on at a sort of fundamental level. But what we actually end up saying is that friction can be sort of well modeled phenomenologically by saying, okay, when an object is stationary, the frictional force is some coefficient of static friction times the normal force, or it's actually less than or equal to that when it's static, or when not moving. And when the object is moving, the magnitude of the frictional force is a kinetic coefficient of friction times the normal force, right, which are the models for friction that you've seen before. Now, there is no reason in the world that this should be true. This is not true. This is a phenomenological model. It does not hold for all kinds of situations. It's actually not a great model for a lot of situations, but it's really simple, and it works pretty well in a lot of cases. And for that reason, it's a good model to use. So friction is an example of a phenomenological force. It's due to E&M interactions, but it's modeled by a coefficient of friction and a normal force. If we think about what the different types of phenomenological forces are, there are a few that we encounter all the time that are worth mentioning. So I'll just make a table of the types of phenomenological forces that you'll mostly encounter. Obviously, one that we've just mentioned is friction, right? Friction is due to bonding between atoms in one object and atoms in another object and having to break those bonds, but the model is very different from that. A second type of phenomenological force that you encounter quite a bit, and a lot of you have seen, is drag and also lift, right? Both of these forces have to do with electromagnetic interactions between an object and the sort of atoms that make up the fluid that the object is moving through. So these have to do with an object moving through fluid. And like friction, there are mathematical models that tell us how big the drag is and how big lift is. But those mathematical models, at the end of the day, are phenomenological models that are based on sort of observed behavior and are based on sort of approximations for how all the atoms in a fluid might be thought of as a continuous medium. So they are very much phenomenological forces that explain observed behavior of objects that move through a fluid. Another type of phenomenological force that we very commonly encounter is the sort of idea of a spring force. So you're familiar with that from, say, for example, design nature, the sort of F equals minus kx type of force. Another force that you'll commonly encounter is what's called a damping force. So this is often actually closely related to drag, but it's sort of the idea that sometimes you have a force that actually is proportional to how fast something is moving. And finally, you have a number of kinds of phenomenological forces that have to do with constraints. So I'll talk about what I will call, in general, constraint forces. And constraint forces are things that basically have to do with the force that keeps an object from doing something it's not allowed to do. So a good example of a constraint force is the normal force, right? I've got one object that's sitting on top of say I've got a book that's sitting on top of a table. There's got to be some force that is pushing up against that object, that book, to keep the book from falling into the table, right? If there weren't some force that the table was exerting on the book, the object would fall into the table. So we call that the normal force. It's called normal because it's normal to the surface. So it's not normal in the sense that it's not odd, it's normal in that it's not parallel. That is, it's perpendicular to the surface. And it's a constraint force in that it keeps things, sort of keeps objects from overlapping. Right? And you can think about why that's the case from an electromagnetic perspective. From an electromagnetic perspective, if I have the book that has its atoms in it and the table that has its atoms in it, and I tried to push down too hard, what I'd be doing is bringing this atom too close to this atom, and there would be a very strong electromagnetic repulsion between the two that would keep that from happening. You can also think about tension as a constraint force. So when I've got some object that's hanging on a string, right, there's some tension T in that string. Why is that tension T present? Well, that force is the force that is necessary to keep this string at a constant length. In other words, it's the force that is necessary to keep the string from breaking, right? So tension sort of keeps stuff from breaking. Or if you think about this as being a case where it's actually, say, a rod that's connecting this object to something, you could also imagine having a negative tension, so you could have compression, a compression force as well, which keeps something from breaking. And in general, whenever you've got some sort of mechanical setup that constrains an object to move in a particular way, there's going to be a constraint force that's associated with that keeps the object in the place that it's supposed to be. So another example of a constraint force is if you think about having some object, say a rod, that is connected via a pin to some other object. There is a pin force here because the pin has to exert some force on the rod to keep the end of the rod fixed here. So constraint forces are the kinds of forces that basically keep objects from overlapping or keep objects where they're supposed to be. They're due to electromagnetic interaction. So you can imagine, again, the atoms inside of the pin versus the atoms inside of the rod that's hanging. You have forces that are due to objects moving through fluids, drag and lift, and damping forces tend to be those types of objects. Spring forces commonly are encountered in a lot of situations. Those also are due to electromagnetic interactions. With a spring force, you're sort of trying to pull atoms a little bit apart from each other, and that causes a restoring force. And finally, friction is another example of a phenomenological force. Now, where we should go next is actually talk about what the mathematical models are for each of these, but I think I'll end this clip here just at outlining what these different phenomenological forces are.